December 7, 1941. Pearl Harbor burns. Japanese Zeros dominate the skies with supernatural agility, their pilots seemingly invincible. American commanders watch in horror as their aircraft fall like wounded birds, outmatched and outmaneuvered. The Japanese Empire appears unstoppable, their air superiority absolute. But within 3 years, everything would reverse. Japanese aircraft would fall from the sky in numbers that defied logic. Not from American bullets, not from superior tactics. They were being destroyed by an invisible enemy that no pilot could see, no engineer could predict, and no commander fully understood until it was too late. This is the story of the hidden war beneath the war. A battle fought not in clouds and dogfights, but in fuel tanks and engine blocks. A scientific conflict where chemistry determined who lived and who died, where molecular structure proved more deadly than machine guns, and where the difference between 87 and 100 octane wasn't just a number, it was the margin between victory and annihilation. The secret that decided the Pacific War wasn't courage. It wasn't even technology. It was something far simpler, far more fundamental, and far more devastating. And Japan never saw it coming. The molecule that changed everything. Before a single shot was fired in anger, the war was already being won in the oil refineries of Texas. While Japanese engineers perfected the Zero's maneuverability and American designers struggled with early fighter prototypes, a French chemist named Eugene Houdry was creating a weapon more powerful than any bomb. He just didn't know it yet. Houdry had fled to America in 1931, obsessed with a seemingly mundane problem: how to extract more from crude oil. In his laboratory at Sun Oil Company in southeastern Texas, he developed what would become known as the Houdry process, a catalytic cracking method that could transform worthless petroleum sludge into something revolutionary: 100-octane aviation gasoline. The process was dismissed by Shell oil executives as Doolittle's million-dollar blunder, when aviation legend Jimmy Doolittle championed it. After all, this new fuel cost 100 times more to produce than standard automotive gasoline. Who would pay for such an expensive product? But Doolittle understood what others couldn't see. Octane rating wasn't about energy content, it was about control. High-octane fuel resisted premature detonation under compression, allowing engines to withstand enormous manifold pressures without destroying themselves. An engine running 100 octane could operate at 65 inches of manifold pressure, more than twice the power of a normally aspirated engine, without the fuel exploding before the spark plug fired. This meant dramatically more horsepower from the same size engine, higher speeds, and crucially, the ability to maintain sea-level power at 20,000 to 30,000 feet where battles were won and lost. In 1938, after years of Doolittle's relentless lobbying, the U.S. Army Air Corps and Navy standardized on 100-octane fuel. Suddenly, there was a market. Refineries began converting. By 1940, when the Battle of Britain erupted, the first Houdry process plant came online, producing gallons of what would essentially become liquid victory. The British Spitfires and Hurricanes, which had been struggling against Luftwaffe fighters running on 87-octane fuel, were suddenly transformed. Filled with American 100-octane gasoline, later refined into the specialized BAM 100 formula for the Rolls-Royce Merlin engine. A Spitfire gained 25 to 34 miles per hour at different altitudes. More importantly, it could climb higher and faster. German pilots couldn't comprehend what was happening. These were the same aircraft they had dominated over France just months earlier. How were Spitfires now climbing above them, attacking from altitude advantages that should have been impossible? The answer lay in their fuel tanks. When the Germans finally captured an intact Spitfire in occupied Belgium and tested its fuel, their technicians were stunned. The British weren't using 87 octane. And when they tried to use captured British fuel in their Messerschmitt Bf 109ES, the engines couldn't handle it. They weren't designed for such high-octane performance. Meanwhile, across the Pacific, Japan faced a different chemical reality. Their domestic oil reserves were virtually non-existent. What little crude they could extract was of poor quality, suitable only for producing fuel with an octane rating of 87 at best. When the United States imposed oil embargoes in 1940 and 1941, banning the export of aviation motors, high-octane aviation fuel, lubricants, iron, and steel scrap, Japan's fuel crisis became acute. By the time war erupted, Japanese aircraft were running on 91 to 92 octane fuel at maximum. Their engines couldn't take advantage of higher ratings even if they had access to better fuel. They lacked the high-temperature alloys necessary to build engines capable of withstanding the increased pressures. Shortages of nickel and chromium plagued Japanese industry throughout the war, preventing them from developing both turbo superchargers and newer high-compression engines. The molecule war had begun, and Japan was already losing 1 octane point at a time, when engines became bombs. The physics of aviation fuel destruction is brutally simple. Inside an aircraft engine, fuel mixes with air and enters the cylinder. The piston compresses this mixture to tremendous pressures before the spark plug ignites it. In a properly functioning engine, the fuel burns in a controlled explosion that drives the piston down, generating power. But when fuel's octane rating is too low for the compression ratio, something catastrophic happens. The fuel detonates before the spark plug fires. This premature ignition, called knocking or detonation, is an engine's death sentence. The fuel explodes chaotically while the piston is still moving upward, creating a shock wave that hammers against the piston crown with devastating force. The explosion creates temperatures exceeding 3,000 degrees Fahrenheit in microseconds. Pistons crack, cylinder heads warp, connecting rods bend, engine blocks shatter. What was designed to be a precision dance of controlled combustion becomes a self-destructing bomb. For Japanese pilots, this wasn't a theoretical problem, it was a daily terror. Their 91 to 92 octane fuel meant their engines operated on a knife's edge. Any attempt to push their aircraft to maximum performance, any sustained high-power climb, any prolonged combat maneuvering risked engine detonation. Japanese engineers compensated by using water methanol injection systems, which cooled the combustion chambers and helped prevent knocking. But this added weight, complexity, and yet another system that could fail. The injection systems themselves required precious materials in short supply. And when they failed, and they did fail frequently, pilots found themselves nursing wounded engines thousands of miles from home base over hostile ocean. American pilots faced no such limitations. By late 1943, U.S. aircraft were running on 100/130 octane fuel, the first number indicating performance in lean mixture, the second in rich mixture conditions. Some fighters were testing 150 octane fuel by 1944. The practical implications were staggering. A Pratt & Whitney R2800 engine in a Corsair or P-47 Thunderbolt could safely operate at manifold pressures that would have torn a Japanese engine apart. American pilots could use war emergency power, deliberately overboosting their engines for short periods to gain crucial speed or altitude advantages. Knowing their fuel could handle the punishment, the R2800 was rated at 2,000 horsepower, the Packard Merlin at 1,750. Japanese engines rarely exceeded 1,500 horsepower, and achieving even that required water methanol injection and careful throttle management. The disparity only widened as the war progressed. When Japan seized the oil-rich Dutch East Indies in their southern expansion, they believed their fuel problems were solved. But the crude oil from these fields still required refining into aviation gasoline, and Japan lacked both the refinery infrastructure and the technical knowledge to produce high-octane fuel. Even with captured oil fields, they struggled to produce anything better than 92 octane. Worse, American submarines began systematically destroying oil tankers attempting to transport crude from the East Indies to Japan. By mid-1944, fuel shortages became critical. By 1945, Japan was so desperate they were mixing aviation gasoline with pine root oil and other improvised substitutes. These ersatz fuels were so contaminated with impurities that American Jeeps using captured Japanese fuel during the occupation suffered immediate engine failures. The quality difference became a feedback loop of destruction. Low-octane fuel limited engine performance, which forced Japanese designers to sacrifice protection for range and maneuverability. This made their aircraft lighter and more agile but also horrifyingly vulnerable. Captured Zeros analyzed by American engineers revealed the truth. Japanese aircraft had almost no armor protection, no self-sealing fuel tanks, and structural designs optimized entirely for offensive capability. A few hits in the right place and they became flying coffins. The structural weakness they couldn't fix. But fuel wasn't Japan's only invisible enemy. The very materials they built their aircraft from were sabotaging them from within. While American aircraft were constructed from aluminum alloys strengthened with strategic metals like chromium, nickel, and molybdenum, Japanese engineers faced a nightmare. Their aircraft industry had virtually no access to these critical materials. The same embargoes that strangled their fuel supply also cut off their metallurgical lifeline. This forced impossible choices. Japanese engineers became masters of lightness by necessity, not preference. They designed aircraft with thinner aluminum sheets, fewer structural supports, and minimal redundancy. The famous Zero achieved its remarkable range and maneuverability partly through brilliant engineering, but also through structural compromises that would prove fatal. When American pilots discovered a captured intact Zero in the Aleutian Islands and tested it, they were shocked by how flimsy its construction actually was. The airframe lacked the robust internal bracing of American fighters. The skin was thinner. The metal itself was of inferior quality, more prone to stress fractures and metal fatigue. These structural weaknesses created a cascading series of problems. Battle damage that American aircraft could absorb became catastrophic for Japanese planes. A burst of .50 caliber rounds that would damage an American fighter's wing might punch straight through a Zero structure, severing control cables or triggering structural failure. Even minor hits could compromise the aircraft's integrity enough that it couldn't withstand the G-forces of combat maneuvering. And without self-sealing fuel tanks, another victim of material shortages, any hit near a fuel tank turned the aircraft into a fireball. American pilots developed a grim nickname for Zeros and other Japanese fighters, Flying Zippos. The material shortages extended beyond the airframe. Engine components required high-temperature alloys to withstand the tremendous heat and stress of operation. Without adequate nickel, chromium, and other strategic metals, Japanese engine components were prone to premature wear and catastrophic failure even under normal operating conditions. Turbine blades cracked. Cylinder heads warped. Crankshafts developed stress fractures. Japanese maintenance crews performed miracles keeping aircraft flying, but they were fighting a losing battle against metallurgy itself. By 1944, the situation became desperate. Japanese factories were producing new fighters like the Kawanishi N-1K Shirden and Mitsubishi J-2M Raiden that theoretically approached the performance of American F-4U Corsairs and F-6F Hellcats. Captured examples tested in the United States received surprisingly positive evaluations when fueled with American high-octane gasoline. But when operating on Japan's low-octane fuel and constructed with inferior materials from a workforce increasingly composed of untrained replacements, these aircraft never reached their potential. Quality control collapsed. Tolerances weren't held. The long V-12 crankshafts couldn't be machined precisely enough. Line boring of main bearings was inconsistent. What looked impressive on paper became unreliable death traps in practice. The most tragic irony was that Japanese engineers understood exactly what they needed. They had studied turbo-superchargers and knew they could match or exceed American high-altitude performance. They had designed engines capable of using higher-octane fuel. They had blueprints for stronger airframes with better protection. But understanding the problem and solving it required materials they simply didn't have. By the time they captured German technical documents on advanced metallurgy and jet engine technology, it was too late. Their industrial base was being systematically destroyed by B-29 raids. Their remaining skilled workers were drafted to fight on the ground, and their supply lines were severed by American submarines. The knowledge existed. The capability didn't. The logistics nightmare N-01 predicted. Even when Japanese aircraft managed to survive their structural and fuel limitations, they faced another invisible enemy, the complete collapse of their logistics system. Japan's military leadership had made a catastrophic miscalculation when planning for war. They assumed conflicts would be short, decisive affairs fought from well-established bases with prepositioned supplies. They had studied aerial tactics with religious intensity but had virtually ignored airfield construction techniques, maintenance infrastructure, and supply chain requirements. This wasn't incompetence. It was a fundamental misunderstanding of modern warfare's industrial nature. In December 1941, when Japan launched its surprise attacks across the Pacific, their air forces operated from superb bases. The Navy's 22nd Air Flotilla supporting the Malayan invasion flew from 3 well-developed airfields around Saigon. Units were at full strength. Fuel and spare parts were abundant. Aircraft underwent thorough 150-hour maintenance overhauls like clockwork. Zeros could achieve their full potential because the logistics chain supported them. But this infrastructure existed only in the rear areas. As Japanese forces pushed into undeveloped territories across the Pacific and Southeast Asia, everything fell apart. The 4th Air Army operating in New Guinea became a case study in logistics failure. Heavy equipment for engine changes and major structural repairs was either absent or inadequate. Depots capable of performing critical maintenance were scattered and distant. The main aircraft repair base at Halmahera sat 1,000 miles from the front lines and never functioned adequately due to equipment and mechanic shortages. Periodic inspections fell behind schedule. Routine servicing became impossible. Aircraft that could have been easily repaired in rear areas were abandoned during advances or retreats. The tropical environment became an active enemy. High humidity corroded metal parts and wires, electrical equipment grew fungus, and the poor quality aviation fuel available in forward areas caused chronic engine problems. American intelligence officers who examined abandoned Japanese airfields after recapture were stunned by what they found. At Clark Field in the Philippines, initial counts topped 500 aircraft, many seemingly ready to fly but grounded by missing components. Huge numbers of carburetors, fuel pumps, generators, and propellers were scattered in fields, buried under houses, or hidden in no discernible pattern. Mechanics had buried tools randomly, making organized repair impossible. It was chaos masquerading as an air force. The Japanese simply hadn't experienced the logistical challenges that Western powers had learned during World War I. They were improvising on an industrial scale and failing catastrophically. The contrast with American logistics was devastating. The United States didn't just build more aircraft, they built entire systems to keep them flying. Mobile maintenance units could set up complete repair facilities near front lines. Specialized transport ships carried spare parts categorized and cataloged for rapid deployment. If an engine failed, a replacement was on its way within days, not months. American pilots knew that if they could nurse a damaged aircraft back to base, it would either be repaired or replaced quickly. Japanese pilots had no such confidence. A mechanical problem in a forward area often meant permanent loss of the aircraft, even if the damage was minor. The fuel shortage compounded everything. By mid-1944, aviation gasoline became scarce enough that training programs were devastated. Army trainees flew gliders during their first month to conserve fuel. Combat units began teaching fuel conservation techniques as early as late 1943, not because they wanted to fly efficiently, but because they had no choice. When fuel shortages finally impacted combat operations, they hit with brutal efficiency. Aircraft sat grounded with full ammunition but empty tanks. Missions were canceled. Critical air cover couldn't be provided. And as American air activity reached its peak in 1944 to 45, Japanese air forces could barely respond, not from lack of courage or pilots, but from lack of the fuel to put them in the air. The human cost of chemical warfare. While Allied pilots accumulated hundreds of flight hours before entering combat, many in actual operational aircraft, Japanese training programs collapsed into a death spiral of inadequacy. Japan had started the war with superbly trained pilots, veterans of campaigns in China who had honed their skills against inferior opposition. These men were artists of aerial combat, capable of extracting every ounce of performance from their aircraft despite fuel and structural limitations. But Japan made a fatal strategic error. They kept these experienced pilots in continuous combat rather than rotating them back to train new generations. Expert pilots inevitably died in combat, and there was no system to replace them. The numbers tell a devastating story. Japan trained approximately 61,000 pilots during the entire war, nearly half of them in 1944 alone, far too late to matter. Of these, 40,000 were killed, many in accidents rather than combat. The accident rate itself reveals the training program's inadequacy. Pilots were rushed through abbreviated courses, given minimal flight hours, and sent into combat woefully unprepared. By late 1943, the average Japanese pilot entering combat had dramatically fewer flying hours than his American counterpart. He had less understanding of aircraft systems, less practice in aerial gunnery, and crucially, almost no experience dealing with the fuel and mechanical issues that plagued Japanese aircraft. American training followed a completely different philosophy. Combat veterans were systematically rotated into instructor positions, ensuring that hard-won tactical knowledge transferred to new pilots. Training programs were continually upgraded based on battlefield lessons. Beginning in 1943, American pilots entered combat with hundreds of flight hours, taught by veterans who had survived the crucible. They knew not just how to fly, but how to exploit their aircraft's advantages. Superior fuel meant they could use war emergency power without fear, better construction meant they could absorb battle damage, and reliable logistics meant mechanical problems wouldn't strand them in hostile territory. The disparity in training combined lethally with fuel quality issues. Japanese pilots, even when skilled, couldn't push their aircraft to the limits. They had to baby their engines, constantly monitoring for signs of detonation or mechanical stress. They couldn't execute certain aggressive maneuvers because the structural limitations of their aircraft made them too dangerous. They couldn't pursue damaged enemies as far because fuel conservation was paramount. Meanwhile, American pilots in their Hellcats, Corsairs, and Mustangs could fly aggressively, knowing their aircraft could handle the punishment. They could pursue damaged enemies across vast distances. They could climb above Japanese fighters and attack from altitude advantages. The fuel in their tanks gave them options Japanese pilots simply didn't have. By 1944, the quality gap became a massacre. Japanese pilots were flying advanced aircraft like the Ki-84 He-8 that should have been competitive with late-war American fighters. When tested after the war with American high-octane fuel, captured Ki-84s amazed U.S. test pilots with their performance, some comparing them favorably to the P-51H and P-47N. But in actual combat, flown by poorly trained pilots using low-octane fuel and suffering from quality control issues in manufacturing, these aircraft never realized their potential. The experienced pilots who might have extracted maximum performance were dead. The fuel that might have let them compete didn't exist. The logistics that might have kept them maintained had collapsed. And the pilots at the controls were, increasingly, barely trained teenagers on suicide missions. The final equation. The true genius and terror of America's invisible weapon was its multiplication effect. High-octane fuel didn't just make engines more powerful. It created a cascade of advantages that compounded exponentially. Better fuel enabled higher compression engines. Higher compression enabled more power per pound of engine weight. More power enabled faster speeds and higher altitudes. Higher performance enabled tactical advantages. Tactical advantages enabled air superiority. Air superiority enabled everything else. Consider the complete system. An American F-6F Hellcat pilot taking off from a carrier in 1944 flew an aircraft powered by a Pratt & Whitney R2800 engine running 100/130 octane fuel. This gave him 2,000 horsepower to work with. His aircraft could absorb battle damage thanks to robust construction using high-quality aluminum alloys. It had armor protection for the pilot and self-sealing fuel tanks. The pilot himself had 300-plus hours of flight training, including extensive gunnery practice and tactical instruction from combat veterans. He knew that if he suffered mechanical problems, the carrier had full maintenance facilities and spare parts. If he was shot down, elaborate search and rescue operations would attempt to recover him. Now consider his Japanese opponent. S-0 pilot in 1944 flew an aircraft with a 1,130 horsepower engine running 92-octane fuel mixed with improvised substitutes. His airframe was structurally weak, with no armor protection and non-sealing fuel tanks that turned into firebombs when hit. He had perhaps 100 hours of flight training, much of it in obsolete aircraft or gliders to conserve fuel. He knew that any mechanical problem would likely result in aircraft loss because spare parts were virtually non-existent. If he was shot down, rescue was unlikely, Japan's logistics were too overextended. And critically, he knew that his fuel supply was so limited that even if he survived this mission, his unit might be grounded next week for lack of gasoline. The psychological impact was devastating. American pilots flew aggressively because they could afford to. Their aircraft could take hits and keep flying. Their engines could handle combat power settings for extended periods. They had fuel reserves to maneuver and chase. Japanese pilots flew defensively because they had no choice. They husbanded their precious fuel. They avoided situations where engine stress might cause detonation. They broke off engagements earlier because every unnecessary minute in combat was fuel wasted. The Americans fought to win. The Japanese fought to survive. And in aerial combat, that difference is everything. By late 1944, the chemical warfare reached its inevitable conclusion. American bombers could reach Japan itself, flying at altitudes Japanese interceptors couldn't effectively reach. Not because Japanese fighters couldn't physically fly that high, but because their engines couldn't maintain power at those altitudes without fuel that didn't exist. The B-29 Superfortress, running on high-octane fuel and equipped with turbocharged engines using advanced metallurgy, operated with near impunity. Japanese fighters attempting interception burned through their limited fuel supplies climbing to altitude, often achieving only a single attack run before having to break off. Many Japanese pilots found themselves gliding home on fumes, hoping to reach base before their engines died. The final tragedy was that Japanese engineers understood everything that was destroying them. They had the knowledge, the designs, even captured examples of Allied technology. But knowledge without resources is powerless. The molecules they needed, the petrochemicals for high-octane fuel, the alloys for better engines, the materials for robust airframes, were interdicted by submarine warfare, destroyed by strategic bombing, or simply unavailable in the quantities required. They were fighting a war where chemistry had become destiny, where the periodic table determined victory, and where the invisible properties of fuel molecules proved more decisive than all the courage of their pilots. The hidden reason Japanese aircraft fell from the sky wasn't poor design or inadequate pilots. It was octane ratings, metallurgical limitations, and logistics failures creating a perfect storm of technical inadequacy. While Americans built an industrial system that could deliver 400,000 gallons of high-octane fuel monthly by 1944, Japan struggled to produce enough 92-octane fuel to keep training aircraft flying. The war in the Pacific was decided long before the atomic bombs fell. It was decided in Texas oil refineries, in Houdry's catalytic crackers, in the molecular structure of tetraethyl lead additives, and in the simple, brutal mathematics of octane ratings. Japan lost the Pacific War to an enemy they could never defeat: chemistry itself. The sweet smell of high-octane fuel burning in radial engines became, quite literally, the smell of victory. And for those who fought without it, every mission was a desperate gamble against invisible enemies lurking in their own fuel tanks, waiting to transform their engines into bombs at the worst possible moment. That's the hidden truth of World War II aviation. The war was won and lost not just in the skies, but in the chemical composition of what filled the tanks of those who flew there.